Um, yeah, thank you everybody for joining today's ELISA seminar talk. We're very delighted to have Ivan Perez from NASA Ames Research Center to give us a talk on the road to safe space exploration. So with that, I'll hand over to Ivan.
Thank you. Thanks, Ben, for that introduction. And thanks everyone for joining today again. Sorry for those of you who came last time, sorry about that hiccup, but I'm glad that you're back and I hope this is interesting to you. So I'm a contractor working at NASA Ames. I've been working at NASA for almost 6 years. And today I want to talk a little bit about the challenges of safe space exploration and also new challenges that are emerging in that arena. So obviously the goal is that safe exploration should be safe for humans and for machines. The missions that we put out there are expensive and complicated, and of course we don't want them to fail. And when we talk about safety in this domain, it's not something that we can approach only at one stage in the mission. It's not like you can look at the software and say verify it or analyze it really well and then you're done. Safety is something that you have to approach and keep in mind at all stages throughout the mission, from planning, safety case analysis, to the design of the mission, analyzing the faults that could take place at different stages in different areas, the implementation, of course, testing, and also in operation. And it's not something that you only look at the tool level and then say, well, if the implementation that I'm working with or the code that I'm working with or the tools that I work with are safe, then I know I'm going to be okay, or even just the machines that I'm working with. If I test them and I determine that they're safe, then I'm good. Safety also plays a role in training people. You need to know that the people that are working on the mission understand the process that you're following and understand what they need to look for. And there's also processes that we need to follow. And we need to ensure that those processes deliver safety as well. And NASA has specific processes, for example, for how we develop software and that are geared towards ensuring that we don't make a certain class of errors. The landscape is changing. Space is becoming more complex. There are more companies going out. There are more complex machines being sent out. We're going further and further away. We're going to need more autonomy. We're sending more complex hardware. So everything's becoming more and more and more complicated. And if you look at space exploration, say 50 years ago, it was mainly dominated by just a handful of players, mainly government-backed organizations. And what's happening now is that there are also companies going out there. They kind of normally coordinate with governments, but they also have a lot of leeway. And that also means they don't necessarily follow the same processes that have been followed by, say, NASA, for example. They have their own processes, and they do have to deliver safety, but they're their own thing. So in all these realms, everything's becoming much more complicated, much more difficult to manage. And there are different ways that you can ensure that, for example, the software that you create or the systems that you create are safe. One thing, if you narrow it down to the level of the hardware of the software, what you could do is you can come up with a model of the system and then test that model or evaluate that model or verify that model. So, for example, you could come up with a model and use model check-in to ensure that in all possible scenarios, something is true, something holds. A property, a desirable property, is always true, right? You could also use model-based systems engineering to ensure that you're deriving this properly, or at some point you can also use testing, of course, which we have historically used and will continue to use. But your model is only as good as how reliably it represents the system under study. And coming up with formal models of very complex systems is not tractable at this point. It's really too complicated for the kinds of systems that we are deploying. So formal models of real world systems are rare because they're so expensive. And testing is only as good as the tests that you actually run. And depending on how you have built your system, there's not even necessarily a guarantee that if you run a test once and it works, it's going to uh, behave the same way next time you run it. Machines have wear and tear. Also, software may not be deterministic. So just because you run a test doesn't mean that it's going to work next time. And tests are not exhaustive. They don't exhaust all possible states and all possible inputs normally. It depends on the system, of course. But as systems become more and more complex, as they operate for longer, then it becomes harder and harder to use traditional methods to assure the next generation of space systems and the next generation, let's say, of robotics, for example. And this is where runtime verification comes into play. So this is kind of focused on what I do here. Um, Runtime verification is a technique in which, together with your main system, it could be your aircraft, your robot, etc., you deploy an additional side system that could be running either on the same CPU or a different CPU that is monitoring everything that's happening and making sure that certain faults do not occur or that certain properties hold at all times. Runtime monitoring itself only concerns itself with detecting the property. When we talk about runtime monitoring or runtime verification, they're kind of interchangeable terms. I'm not talking about how to fix the problem. That's very mission specific, and I cannot give you a framework that will solve all of those problems. But my goal is to give you a way of detecting the problems. As I said, the expectation is that these monitors will check everything that's happening with the mission, but sometimes we may also want to monitor the environment where the robot, the aircraft, the payload is operating. It's common, for example, that we reuse something from one mission for another mission, and there are certain assumptions that go with it. So you want to make sure that those assumptions are carried with your software. And there have been, not NASA as far as I know, but there have been big space missions that failed for those reasons. We may also be operating in an environment that we don't know well enough. So we may want to also monitor not just what's happening with the vehicle, but also what's happening with the environment, because we think the pressure is going to be this much or the temperature is going to be this much and so on and so forth. And that's not true. And so if something is not working, we need to know if it's because we didn't do it well or because the environment is much more different from what we thought it would be. And the monitors can be deployed in the vehicle itself, with the robot or with the rover, or they can be running in some sort of ground station. It's not uncommon that we'll have the monitors installed and just getting all the data from the vehicle and then looking at that data. There are different techniques in runtime monitoring. If you read the literature, you'll find that some people just log the data and then analyze it. But for the purposes of this talk, I'm focusing on online runtime monitoring. And that means the monitors run alongside the system and make decisions on the fly. Kind of what I want to convey about this is that runtime monitoring is sort of the last line of defense, because runtime monitoring is there to detect the things that you didn't design your system to handle without the monitors. You didn't formally verify, you didn't test for or couldn't test for, or the tests did not always catch. And you don't have many more ways of detecting those unwanted situations and dealing with them, which also means if the monitors fail to detect something that should have been detected, it's a fault or an unwanted situation, then you may put your mission in danger. If the monitors give you a false positive, which is they say, yeah, there is a problem, and there isn't, you might ground your mission unnecessarily. You might take some sort of evasive or corrective maneuver unnecessarily that could also put you in danger or could cost you a lot of money. So you don't want any of those errors to take place. And that means we pay a lot of attention to ensuring that the code that we generate for the monitors is correct, and also that people cannot easily introduce errors in the monitoring code. And that's, excuse me, the kind of the point of the first half of this talk. In the second half, I will focus more on other methods that we use to ensure that the code that we develop is correct. So at NASA, I developed a tool called Ogma. And the purpose of Ogma is to take a specification in a high-level language and to generate the monitoring code. And the sales pitch, if we do it right, is that the monitoring application will be ready to be deployed. And that means you may have to talk to it to detect when the violations take place, but you won't have to modify it. You just have to drop it somewhere and then connect it to the rest of your ecosystem. And if you zoom into Ogma, Ogma is just a translation tool. It takes specifications in high-level languages, and then it produces code in a number of possible targets. The main source of Ogma is Copilot. Excuse me. Copilot actually works as a source and as a target. You can take one of the other languages supported and generate Copilot as a monitoring specification, or you can take a monitoring specification in Copilot and generate C99 and so on and so forth. So to give you some context, these tools work kind of hand in hand, and Copilot is a runtime monitoring language. I know that GitHub has their own system they have called Copilot, but this predates GitHub's. And it is a runtime monitoring language for aerospace and for hard real time. And I'll give you a few more details about Copilot later. But the idea is that you feed one of these sources of properties in one of these languages, and Ogma is going to give you either a C99 implementation or that together with a NASA core flight system application that is ready to run on NASA systems, or a robot operating system node specification, and so on. And as I said, these tools work kind of hand in hand. They're both open source. Copilot is a hard real-time runtime monitoring language, and it produces C99, or it can produce an FPGA. The FPGA backend is experimental. If you want to try it, I think we can give you access, and I'd be happy to get feedback on that. Of course, I'm also happy to get feedback on the C99 backend. And Ogma is kind of Copilot on steroids. What Ogma does is it leverages the capabilities of Copilot to make the application ready to run in the target system. So where Copilot only gives you like a variable C99 module where you pass the data and call a function in C and then declare handlers for the violations, Ogma is able to connect that with the rest of the ecosystem where you're running. As I said, part of what we pay a lot of attention to is ensuring that the code that we generate is correct. So what these tools try to do, and the direction that we're going, is not only generating the C implementation or the C++ in ROS, or depending on the platform, is also generating the evidence that people would need to evaluate that code and determine that it's safe to use. So there's a new extension. This was presented at ICFP, the International Conference on Functional Programming, just 3 months ago or 4 months ago. And there's an extension to Copilot that, together with the C code, it generates a formal proof that that C code is correct. And what I mean in this particular case by correct is that if you take the Copilot specification and run it through the Copilot compiler and get the C code, if you compile that C code with LLVM and look at the intermediate representation in the LLVM compiler, the behavior of that intermediate representation and the behavior of the original Copilot specification is equivalent. That they kind of behave the same way at all times. And it gives you a formal proof of that. There's an abstraction over the LLVM intermediate representation, and there's a formal proof that the two will behave the same way. And we're now looking at other evidence that we could generate together with that, including tests, coverage, and so on. As I said, both projects are open source. Ogma is part of the NASA organization on GitHub, and Copilot has a dedicated organization called Copilot Language. NASA has its own classification for software that determines how we need to assure and how we need to evaluate the development of software to deliver quality depending on the criticality that we're targeting in applications. Copilot is class D. These classes do not match what you will find in DO 178. So I can point you to the document, but if you Google this particular term, NPR 7150, you'll find the classification. And Ogma is currently going through the process to obtain the same qualification. And what that means is these tools, we expect that they'll be able to generate code that flies. And to fly, you need to be class C. So you can generally, this is not like a hard rule, but generally you can expect that if you're targeting non-critical systems, you can use a class D tool potential to generate class C code. And you'll still have to assure the class C code to the level, but it's going to be a relatively accepted method. And when we start focusing on space, then we'll need to go up to class B and class A. And part of the plans for the current fiscal year and the next one is to go towards those classes, to make sure that the code that we generate can be used in those missions. And both tools are released every couple of months. So this is an example of a property. This is an idealized property. The idea is that if you are flying, you need to maintain a certain airspeed. Imagine, for example, a plane. If you don't fly fast enough, then you're going to go into a stall and you're going to lose control. Essentially, you won't be able to continue flying straight. And the numbers are completely made up. They're just so that they're easy to read. But one way that you could describe this property is that if your airspeed drops below a certain threshold, the autopilot of the aircraft should, in a certain time, bring the airspeed back up. And the way that you could write that in Copilot is, well, if you're in flight mode and the airspeed drops below that threshold, then in a certain amount of time, like eventually in between 0 and 10 steps or seconds, depending on your time unit, the airspeed will recover and be above the threshold. So this language is relatively simple to read. It's meant to be like relatively close to what you would want to write. And it also has a number of mechanisms that you can use to ensure that you're getting the right property. So you can specify properties about your property and then use theorem proving and all kinds of things to analyze them. But the expectation is that most properties will be relatively straightforward to describe. And when you run a collection of properties through Ogma, in this case, we use the ROS backend. As I said, there are several frontends. In this case, we use a different one, but it could be the Copilot one. It gives you the application code. In this case, that application code is plugged into the Explain simulator. And what it does is it checks this property. So let me just run that video again. You see the plane going up, and then I go nose up to bring the plane into a stall. The airspeed drops. And on this side of the screen, you see the monitors running. And at some point, you'll see that it turns kind of on. The fire symbol goes on, and that signals that the monitor went off, detecting a violation. So the widget on the screen, I had to write by hand, but the generation of the monitoring code was completely automatic from this property that you saw here. And Explain is obviously not what we normally use for missions. There are 3 software frameworks that we use, at least as far as I'm aware. There could be others that I'm not aware of. One of them is NASA's Core Flight System. It's also open source. The other is F Prime. Both of them, all 3 of them are open source. F Prime is the one used in the Mars helicopter. NASA's Core Flight System, as far as I'm aware, has been certified up to Class A, which is the highest class that we have. Is the kind of stuff that runs in safety critical systems or that runs in manned space. And the other that we use is ROS, the Robot Operating System. And ROS and CFS kind of work in a very similar way. F Prime is a little bit different, but they are all component-based systems where you write your applications as different components, as different components and then communicate them in some way. My understanding, and I'm no expert in F prime, but my understanding is that in F prime, you kind of declare the systems with input and output ports and then connect them. And in CFS and in ROS, the systems or the sub-applications or the subcomponents that you write in publish data in a software bus. And it could be using message IDs in CFS, or it could be using topics. ROS leverages DDS. So if you have used DDS for communication, it's the same thing. And ROS nodes will publish messages in dedicated topics or in the software bus, and then will subscribe to other topics in the software bus to detect the data. So what Ogma does is, let me see if I can hear. What Ogma does is it generates another component at the same level as the rest of the components of your application. And that component listens to the software bus, and it listens to messages for the kind of data that you've mentioned in your property. And that is what this variable database file is about. It just tells Ogma how to find the data. And it's something that you describe once for your whole system. And what Ogma does is it generates the whole application for you. So the application will subscribe to the topics, get the data. Every time there's a new message, rerun the monitors. And if there are any violations, it will publish the results in a dedicated topic. And that way, it kind of gets the monitoring problem out of your way. It's still your responsibility to subscribe to these guys and determine what to do and how to handle each fault or each violation. But at least the monitoring problem is out of your way. And we also generate additional aids for testing. So one of the things that you can do is you can use the monitors to test your application at design time or at implementation time. So you could imagine how if you have the monitor already, you could run it with sample data and just ensure that the monitor is not firing off, and that gives you some understanding that the applications that you're running and the subcomponents that you're creating kind of behave correctly. So together with the ROS backend, and now we're doing this for the other backends, we also generate testing aids. And in particular, you can take, you can specify that you want to generate a test where you turn on different components together with the monitors. And then you feed random data for some of the message IDs, or in the case of ROS, for some of the topics, which may not be the topics that the monitors are listening to. They may be the topics that other components are listening to. So just generate random data, let the components process it, and put data in the bus, and turn on the monitors to listen to what's coming in the software bus. And the idea is that you leverage the monitors as oracles. So instead of just running them during the mission, you can run them during design and implementation to detect potential violations. And together with this backend, we generate like a testing aid for ROS and a Docker image, a Docker file, that when you run it, will do this. It splits the screen in 3 parts. In one of them, you have an interactive shell so that you can observe the software bus. And in the other, it starts feeding random data to the software bus. And if it detects a violation using one of the monitors, it will print the monitor that was violated, or the property that was violated, together with the seed used for the random number generator and the step of simulation where that happened. And if your code is deterministic, which is kind of up to you, then you should be able to replicate this. This is, by the way, this screen kind of tries to capture the fact that from the same input, we can target all platforms. If you're familiar with any of these, you would recognize these files. From the run that you saw before, depending just by changing the backend, we generate all the files that you need for ROS, including the monitoring node together with the logging node that will just print the violations to the logger just for debugging purposes, together with the testing package. For F prime, we generate a whole implementation, and for CFS, we do the same thing. And if you're familiar with any of these platforms, you'll see that this is pretty much everything you need in any of them to have a full monitoring application and connect it to the rest of your system. So just a few more details about Copilot. I don't want to go into a lot of details about Copilot now. If you're interested in a talk specifically about this, I'd be happy to go into that. But just to give you a few more details, Copilot is a stream-based monitoring language. Think of it as signals coming in the system and signals going out of the system. So the signals coming in the system could be the battery temperature or the airspeed or the acceleration of your vehicle as measured by some sensor. And using that data that changes over time, you process it and produce streams carrying booleans, true or false, representing whether the property holds or is violated. And if you use MATLAB or Simulink, for example, you probably are familiar with that. If you use Lustre, you probably are familiar with that mode of thinking, that data flow mode of thinking. So Copilot is a language embedded in Haskell, and it uses features of the Haskell type system to provide further assurance. And one of them is that it uses dependent types, and Haskell has limited support for dependent types, but it uses what is available in Haskell to provide further assurance. In one case is that arrays, for example, in Copilot have fixed length, meaning when you define that you have a stream that has data of type array, and the elements of the array are integers with 8 bits, you also have to specify how many integers are in the array. You have to say there are 3 integers or 4 integers in the array. And that also means that if you try, for example, to assign or combine values of arrays such that the lengths don't match what you expect, the type checker is going to tell you that the length doesn't match. So if you have a variable of type array 3 elements of type int 8, and you try to assign it a value with array 2 elements of type int, the type checker will tell you that doesn't work. There's a lot of libraries together with Copilot. For example, we have libraries for temporal logics, which is the language that is used traditionally or has been used traditionally for runtime monitoring. We have libraries used for voting, which is used for fault management. We have libraries for regular expressions. State machines is a common case that we see in missions. Clocking, so that you can process data at different speeds. Stacks, statistics, and so on. And we have connections to SMT solvers, and this is something I mentioned earlier, that not only can you write properties about the system that you're observing, you can also write properties about the properties themselves. So you might write a property and say, for example, that it should always increase over time. Maybe you write an expression in Copilot, a stream expression, and you want to say, well, under certain expectations, this expression should always grow indefinitely. It should never decrease. And you could write something like that and then leverage the proof of that property into an SMT solver. And there are several that we support. And as I said, there's a verifier that will check, that will produce a proof that the code that comes out of Copilot is correct. Before I continue, we've been on for almost 30 minutes. Any questions, any comments? You don't have to wait until the end of the talk to ask. So please unmute yourself and go ahead if you have any comments or questions.
No, you're doing good. Thanks.
All right, thank you. So as I said, Ogma and Copilot are released on a fixed schedule every other month. Copilot is released on the 7th every other month, and Ogma is released 2 weeks after. And we've been doing that for years now, since 2021. And we've never missed a day. Like we are very regular at delivering the implementation on time. And we also try to make them available in standard distros. So Copilot is available in Debian and Ubuntu. And kind of the thinking there is that a lot of these tools are very sophisticated, but then they're really hard to get running. And we want these things to be available to everybody and easy to get on board with. And if you try it and you can't get it to work, or you don't understand it, or there's something that limits your ability to use it, please let me know, because I think it's my responsibility as the technical lead of these tools to make sure that we do a better job. Maybe we need to improve the documentation. There's a tutorial that we're missing that we should provide, or there's a platform that is interesting for someone and we're not supporting properly. So I want to know also about your limitations. Don't blame yourself, blame us. So please, if you try it and it's not what you expect, let me know. Open an issue directly on the GitHub. You don't even need to email me. You can just go to the repo and open the issue. And the second part of this talk, I want to talk about process compliance. And as I said at the very beginning, it's not just about delivering tools that will check for these properties and that the tools are produce proofs and so on. It's also about how we produce the software. And just to tell you a little bit, so for example, in Copilot, one of the things that we do is that no change goes into the code unjustified. And that means every single time that we make any change, there's got to be a change request that someone has evaluated and approved, and we mention it in the commit. And there's the history is linear. We enforce linear history always. So you can always look at a change in the history and determine why it was introduced and who did it and who approved it and so on. And I'm going to tell you a little bit more about how we do this and what other rules we follow. So NASA has a process called NPR 7150, is the NASA procedural requirements for software engineering. And it's a long list. I'm not going to give you like an exhaustive description of this, but it's long. It's quite extensive. And some of the requirements have to do with static analysis, and others have to do with how the project manager needs to evaluate whether they develop a tool or they purchase it. So there's a bit of everything in here. But to give you, like I selected just a few here, one of them is the project manager shall develop a software configuration management plan that describes the functions, responsibilities, authority of implementation and configuration management for the project. And this applies to classes A through D. This would be class E, which is the standard class for software that you just do when you're trying things on your own before it's used in any mission or in any experimental work. And here, the one that I mentioned earlier about tracking changes is to meet, like, we meet requirement 80 by doing this. So by implementing this process in our tool, we meet this requirement. The project manager shall track and evaluate changes to software products. So it's part of the way that we implement this. And part of what we saw when we went through this process is that it's really hard for people to, like people within NASA and people that are working with NASA, to understand what is needed to meet these requirements. And we want that process to be more open. We want that process to be faster. We want companies, especially because of what I said earlier, there are more players involved these days. We want to decrease the time to market. And the way that I'm going about it is by trying to share as much as I can about this process, including templates of the documents that we have to fill in, including incorporating some of these ideas into other open source projects, including also the fact that Copilot and Ogma are open source tools. And a lot of the process that we follow is described online. So if you go to the repositories and you start looking through the issues, you'll see the steps that we're following. So I'm going to tell you just a little bit. I'll skip through some of these slides, but I'll tell you I just want to give you a brief overview. So one of the things that we do in these tools is that every time there's a change request, or if we see, say, something that we want to change, something that we want to update, we can't just go and make the change. We also cannot just go open an issue, make the change, and close the issue. There is a process that we have to follow. So issues go through a series of steps, and they are described in this document. So this document is a bit more comprehensive, and we try to leverage as much as we can already from what exists on GitHub and all of these platforms. We try to come up with a process that is open source friendly. So we are asked to baseline our versions so that they can be identified uniquely. And we use standard terms in Git and GitHub to implement this requirement. And this is like our documents internally talk about these tools. They say on GitHub, we're going to use this, and on Git, we're going to use this, and this is how we implement it. And hopefully other people who want to develop their tools as open source, they will be able to start from that template and reuse what we have. In our case, for example, one of the things that in Copilot and Ogma we enforce is that every time there's a new version, like a baseline, like a release, we tag it. We have a branch before the release. We use something similar to Git flow. So before the release, the branch name has to be release dash and the version name. And there's going to be a milestone. And that means every change request that has been incorporated in that release has to be associated with a milestone with the same name. And that allows us to evaluate a certain level of code or obtain a certain level of consistency. And all the versions of all the libraries that we produce use the same tag. So essentially, if you look at both the code and the repo and the GitHub, there's going to be consistency across all of them. And the change requests, we have a template that you can see online, and actually GitHub supports. We don't use it, but GitHub and some of these tools support kind of giving users already a template. But every time there's a change request, we ask people to fill in a description, tell us if it's a bug or something else, any other context, who is requesting that change, and also a way to reproduce that error if it's a bug. And this comes up later, but it's a minimal example that we can use to show that the error is there. And then tell us what they expected. There may be different possible solutions. And we also ask that they tell us, or that they tell us if one of them is preferable, and then if they have any understanding of the code. And this is more geared towards people who work already on the implementation, is what they propose we do about it. Sometimes these sections will point to specific modules and so on, and any other notes that apply. I'll come back to this change request in a minute. But part of that document that you saw earlier also talks about the different roles that we have. And so we expect all of this documentation to be reusable by different missions and even projects outside of NASA. And all the documentation talks about the different roles that different people in the project have, and we introduced a bunch of them. And in terms of change request management, we have a notion of a change manager, a release manager, which is the person that puts the software out there. And then we also have the software developers and the technical lead, which is the person that gives the thumbs up in the end and so on. So how the change request makes it all the way from being filed to actually being put in production, and the software being deployed to or sent to Debian or to whichever repository it is an interaction between these people. And our documents use these roles to talk about them. And let me just go to this. So when there's a change request filed against the system, as I said, we don't just make the change in the code and send the pull request or commit it to the repo. The change goes through a series of stages. So at the beginning, when it's only being filed, we call that initiated. And after that, somebody comes in, the change manager, actually, which I mentioned earlier, comes in, and the role is to confirm that the bug isn't there. And they don't determine if it has to be fixed. They don't determine what we do about it. They just need to tell us, yeah, this is indeed a problem. It could be that we don't have the resources to deal with it. It could be that we don't really care. Once we have determined that we do care and we're going to do something, then the change request becomes accepted. At some point, once we'll deal with it, it doesn't mean that we'll deal with it now. Once we know who's going to work on it and we schedule it for a particular milestone, then it becomes scheduled. And once the developer says, I'm actively working on this, it transitions to under implementation. And eventually, once the developer or developers finish and submit the pull request, transitions to verification. And then once it's accepted, it becomes closed. And how we implement that is we just leverage the tags or the labels on GitHub to signal this. So we just have dedicated labels for each one of them. And when you go through to our repositories, you'll see us do this. You'll see that, okay, there's this change and it has the tag, there's a bug and it's initiated. And then the change manager, in this case, I had both roles. So the change manager comes in and says, yeah, I can confirm that this exists. And then the labels change. And we do the same thing if we decide that we're going to address it. Normally, even though in this case it's the same person, I do this on my own. And for this, I may meet with other people to determine if we really care about this. And the change go through those stages, and eventually the person sends a pull request. And after the pull request, we leave a report that goes through a checklist of the things that we need to ensure that are there before we accept the change. One of them is that there's got to be a successful build in the CI server. Another is that there's got to be a way to reproduce the bug. And for most cases, it doesn't always work, but in most cases, we just provide a Docker image. And the idea is if you run the Docker image on master before the merge, then it should fail. And if you run it after the merge, it should pass. And that's a reasonable test. And then we leave, I mean, they can be very extensive Docker files. And then we evaluate a few more things. For example, that people don't just submit a history that is all squashed necessarily, or that tells us how they figured out the solution, but rather a history that is clean, that tells us how we should incorporate the solution. They shouldn't mix anything that is unrelated to the issue. So if you're modifying a module and then suddenly you realize there's a typo somewhere in the module, but it's unrelated to what you're doing, you're not trying to fix typos, just leave it in, deal with it later as a separate issue. And then there's a few more things. We modify the change logs, examples, and so on. And when we merge, we leave this report also in the repo. So you can go both to the Git history and the GitHub repository and see these reports. And as I said, we want to provide to people tools that they can use to produce this documentation that we need to produce. And now we're trying to make some of this documentation available online as open source for others. But what we have now is a system based on Pandoc, which is, again, an open source tool that takes the documentation written in Markdown, and it produces the file exactly as NASA needs it, with all the right headers and all the right logos and everything. And this is how we did Copilot and how we're doing Ogma. And there's a Docker image that people can use to run these things and generate all the documentation. So we're trying to make some of this work or port some of these ideas now to Space ROS. I don't know if any of you may have heard of it, but Space ROS is kind of a collection of tools and processes and documentation geared towards helping people write robotics applications to be used in space. And if you go now to the Space ROS repository, for example, you'll see that we are following a process where all the changes that are incorporated to the repository are justified. There's got to be an issue for each one of them. The process that we follow there is a little bit more lightweight than the one that we follow for Copilot, because in Copilot we are not leveraging the community to implement the tool. We are using NASA resources for that. We still want people to contribute, but we don't expect most of the development to happen there. And in Space ROS, the expectation is that probably it will be mostly community driven. And that means also the process has to be a little bit simpler. But also the documentation that you saw earlier, these documents that we're producing, we're coming up with kind of a matrix that lists all the requirements that NASA has for different classes and how those could be met potentially in Space ROS applications using the additional checks that are incorporated in Space ROS. So one example is that you have to do static analysis. That's part of one of the requirements. And in Space ROS, you will see that we have enabled and we provide tools to do static analysis on the code. So the expectation is that if you do it following the recommendations, hopefully you will have an easier time qualifying. And this matters if, for example, you're developing software that you want people to have an easier time using for missions, or also because maybe you are working on robotics missions or space missions and you want this code to qualify. And what we're finding, though, is that this process is very thorough. And we've been told by people in other branches at NASA that it's much more thorough than maybe what they would have expected for the class that we're at. But we don't want that to get in the way of compliance, in the sense that if we require people to follow many steps, especially, as I said, for example, people in the open source community, then they're very unlikely to follow it. So what we're looking into now is ways of analyzing the repository and telling us if we're compliant with the process. And the hope is that if we give people the template that they can follow, it's not mandated by anybody, but they can follow to reduce some of the documentation and the process that is described in that document. If they follow that, then the tools will be able to look at the repository and establish or give some sort of evidence of compliance with that process. So the idea would be that it would be much easier for them, rather than trying to come up with their own process and then have the auditors go through the whole system to evaluate whether they complied or not with their own process, and then demonstrate in some way that that process will meet the NASA requirements. Well, you can just use the template, ideally without having to tailor it, and then use the tools to evaluate all the evidence that you have, and then the auditor will be eventually familiar with the process that you're following because it's a template that more and more people are using, and they will have an easier time evaluating your evidence. And this is what we're looking at now. We're leveraging a tool called Kaiaulu that looks at the Git repo, and it works also for Jira and other kinds of software issue management tools and code management tools. But because we use Git and GitHub, that's how we did it so far. We have scripts in Kaiaulu that will look at all the Git commits and all the GitHub comments and pull request comments and label changes and events. And they tell us if, for example, we're following that process of changing labels correctly. And it has detected that in some cases, we didn't change the labels in the right order. And we detect those process deviations. And then we analyze them and we justify to auditors that we are detecting those and putting mechanisms in place to ensure that that doesn't happen again. So it's okay that we make certain classes of errors so long as we are able to detect them and we minimize their impact. And the tool is hopefully will be something that will run with every pull request, just to make sure that before the changes are emerged, that we follow the process as we had described, and that will ensure that we never deviate. And also with every release, we will be able to produce a report that we give both to the community and to the auditors so that they know that we continue to comply. And the tool generates graphs of different kinds. And this is just one example of one thing that we were looking at is not so much about the process, but we wanted to know who was involved in the project. And so by looking at all the Git commits, the tool told us who had worked on which issues. And this is kind of quite an interesting piece of data that it can help you understand if one person is doing too much in a project, and also the risk that you may be assuming by giving that person too much responsibility, because if they have to leave or if they are moved to another mission, then you lose an important member of your team. So in Space ROS, one of the policies that we have enforced now is to have sort of mandatory rotation, meaning that instead of having one person, say, being in charge of releases every time, rather we have one person being in charge of one release and a different person being in charge of the next release. And by having that rotation, we minimize the risk of having a graph like the one that you're looking at on the screen, where this is me in this project and this is a colleague. Between the two of us, we kind of have done most of the work. And like when he left the project, that was a big blow for the team. And it could happen again that if I leave somewhere else, then the project may die. So looking at this data is not just a way of understanding if you're following the process, but also of quantifying and communicating the risk that you're taking. And this is another piece of another graph that it produces. It tells us which people worked on which files, and or sorry, which issues touch which files. I had another which is not represented here, that showed which people worked on which files, and that was very interesting because it told us whether there were any files that nobody was able to work with, and that again helped us quantify the risk that if we lose that member of our team, we won't be able to maintain that file. So if that portion of the implementation is critical, we may force someone else to get educated with that part of the implementation. But just to summarize, the idea is to use these tools to analyze all of this, like the Git repo, the comments, the commits, and everything, so that we can provide evidence that the compliance is being met and also the risk is being limited. So and kind of why this is important is I guess because we're trying to make this a process that everybody can follow. And to tie it back to what I said at the very beginning of the talk is the space, the exploration of space is becoming more and more complex. There are more players, and we need to be able to work with them. And these are companies that need to work in a very agile way, and just trying to get them to follow a very slow process. There's a risk that they won't do it. So to democratize that space, we also need to provide tools that give you a shorter time to market, that allow you to be more agile in a very general, loose sense of the word. I'm not talking about the specific agile methodology, just allow you to move in quickly and to evaluate things quickly and to qualify your tool for flight much more quickly. And that's what these tools try to provide. So they on the runtime monitoring side is a way of dealing with higher complexity without that imposing a huge cost or delay on the mission. And then on the methodology side, tools that will allow you to gather the evidence, to make sure that you always comply with the process, and also to minimize your risk. So that's everything I came to say. If you have any questions, I'd be happy to take them. Thanks.
Thanks, Ivan. Okay, we've got Paul turning the camera on. Do you have a question, Paul? Go for it.
Actually, no. I was just going to say thank you very much. This was very good, and I'm hoping I can get the recording later to show to some of my other colleagues here.
Mm-hmm.
Yeah. And we'll work on getting it posted off of the ELISA site so that people can find it. And then feel free to reach out to her directly. So she's got your email if you want to be pointed to it once it's up in public.
Mm-hmm.
Okay. Yeah, this looks really good. Virago is just starting to get into the A-class processor stuff, and we and Linux and whatnot. So we this looks like some very good tools. So very nice.
Thanks. So if I may ask, what organization did you say was doing this?
Virago Technologies. We're in Austin, Texas.
Okay.
And we do radiation hardened microcontrollers.
Mm-hmm. Okay.
Yeah.
Nice.
Oh, another Austinite.
Mm-hmm.
Yeah. And you're looking at Linux as a platform to.
Yeah, we're looking at that.
Mm-hmm. Something that came up this morning in the ELISA meetings is that we're looking at running the monitors directly at kernel level with eBPF and other ones. You just reminded me of that when you mentioned.
Oh, cool.
Yeah. But this is very early on. So if this is something that anyone in the call cares about, please reach out to me, because I would love to work with you to see how we could come up with monitors that are useful and evaluate them.
We're pretty early, we're learning right now. So, it'd be a little while before we start installing your tools and stuff, but it looks very interesting.
Hey, Ivan, thanks again for the talk. With regards to the last comment you made, I think it'd be interesting to bring some of that discussion about in-kernel monitors to the Linux Features for Safety Critical Systems group. So if you're
Okay.
looking to engage with people in a discussion about it, that might be a good place to start.
Mm-hmm. Okay. Yeah, sounds good.
Well, if there's no more questions, I will say thank you again, Ivan, for doing this. And very much appreciate you taking the time to share this with us in a way that we can share it with others wider.
My pleasure. Thank you for having me, and thanks everyone for attending. I hope this was interesting.
It was.
Thank you.
All right. Thank you.
All
Thank
right.
you.
Bye-bye.
Bye.